Testing. 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 Test. 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 Whoa, lo, 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 lo. Okay. It's working. Alrighty. Welcome to another stream. Hello, Doga Tahan and Majeti Gizzle. How's it going? Today we got a viewer recommended paper for you guys. This is coming from Danielle Mika. This is a diffusion paper. Kind of a weird paper, to be honest. Lots of potential complicated pieces here. Just look at how complicated this pipeline is, but, you know, they use little cats, so how could I say no? This paper, interestingly, so we got learning controllable 3D diffusion models from single view images. And the interesting thing here is that this author, so the person who did most of the work and another person who was close to there, as well as the most senior advisor position, right? So in papers, the first person does all the work, and then the very last person is the most senior person on the project. But these people come from Apple. So I suspect that this is actually what Apple is doing. So it may be the case that whenever you see in a VR headset some kind of rendering of a person, I know these kind of like neural avatars are starting to become popular demos on the VR headsets where basically you can create a version of someone's 3D face. There might be little elements of that in here, right? So I don't know. Could be cool. Could also just be a over-engineered mess. Majeti Gizzle. Pronounce my name right without hesitating or shortening it. Subransu Bhattacharjee is the code out. It's coming soon. I don't know what the fuck, if this is some kind of joke. Coming. But no, it is not. The link for this is literally just a link to this website. Jiao Gu. Let's see if maybe we can go to this guy's GitHub repo. 2 contributions in private repositories. You see this? July 17th, July 18th. So he's committing to private repositories, so I bet you the repo for this is just private, so it hasn't come out yet. Yeah, they probably just, you know, the Apple part is I think the missing piece to the puzzle. I'm sure that they released the paper and then they were going to release the code, and then it turns out that they use some utility functions or some libraries that are proprietary to Apple, and then in stripping out those libraries, they realized that the code doesn't work anymore, so then they realized, okay, well, we can't actually ship this code, which is something that happens all the time in big tech companies. When you try to publish the code, if you ever use any libraries or code that is actually secret inside that tech company, then you basically have to either re-implement it specifically for the purpose of releasing your paper, or you have to figure out how to basically convince people to open source that part of the code as well. And that's usually a huge mess, and generally the way you're incentivized as a researcher in these big companies, you're just as good as your next project, so it's not worth fighting it. So my guess is that that's what happened, is they were going to release the code. They realized that there's a couple different things that they can't release, and then rather than release broken code, they just said, hey, forget about it. That would be my guess. Subransu, but we'll see if it's worth actually looking at the code, though. So let's see. Diffusion models have recently become the de facto approach for generative modeling in the 2D domain. However, extending diffusion models to 3D is challenging. Yeah, I agree. due to difficulties in acquiring 3D ground truth data for training. Yeah, and it's not just the difficulties in acquiring that 3D ground truth data, but I think it's also there's not agreed upon convention for 3D data yet. You know, we've got nerfs are starting to become popular. You have meshes and textures. There's a lot of different ways to represent 3D information, and so far none of them are necessarily good for learning-based approaches. I guess other than nerfs, but nerfs are still new enough that there isn't huge nerf datasets yet. On the other hand, 3D GANs that integrate implicit 3D representations into GANs have shown remarkable 3D aware generation when trained on single view image datasets. So GANs here are generative adversarial networks. They're kind of an older technology at this point, but you could think of them as basically two networks that kind of fight each other. You know, you have a generator and then you have a discriminator, and they go back and forth and back and forth and back and forth, and eventually you end up with a generator that can generate pretty good images in one shot. So unlike a diffusion model, which takes multiple steps of noise removal, a GAN can generate things in one shot. It can also be conditioned on a variety of different things. But they've kind of fallen out of favor. We've seen a couple papers here and there that will try to bring them back up, but diffusion models are kind of running the show right now. And single view image datasets, single view just basically means one shot, just one picture. So you can see here in this, you have input is just this picture of Einstein. So that's a single image, single shot, single view. Subransu, pose encoding is hell. I was trying to find a method to do that. Neural nets are just not smart enough to understand data categories. Yeah, the way to encode 6D position information is still definitely not standardized. However, 3D GANs do not provide straightforward ways to precisely control image synthesis. This is not necessarily true. There are ways where you can disentangle the latent space of a GAN and then be able to manipulate the generation of images from a GAN. To address these challenges, we present Control3Diff, a 3D diffusion model that combines the strength of diffusion models and 3D GANs for versatile, controllable 3D aware image synthesis for single view datasets. Cool. So, I mean, this is like a big jargle of words here, but none of these words really necessarily mean anything. Versatile doesn't mean anything. Controllable just means you're conditioning it on something. 3D aware also doesn't necessarily mean anything. Image synthesis, they're just generating images. Control3Diff explicitly models the underlying latent distribution. So generative adversarial networks, when I say disentangling the latent space, there's some latent space that contains the distribution from which samples will be drawn and images will be generated. And it seems like this approach, their Control3Diff, is going to model the distribution in that latent space, which will be conditioned on external inputs, probably some kind of 3D prior, thus enabling direct control during the diffusion process. Moreover, our approach is general and applicable to any type of controlling inputs, allowing us to train it with the same diffusion objective without any auxiliary supervision. Different types of controlling inputs. Okay, so they're probably going to try to condition on a couple different things here. So we have edge maps. This is kind of reminiscent of ControlNet. You got text, of course, everybody's favorite text, probably embedded with clip. If you guys want to start taking bets, I'm sure they embed that with clip. And SR plus 3D, I think SR just refers to super resolution. And then it kind of looks like the output for every single one of these examples is basically the original image, but with the view direction changed, which seems like something that would be very useful if you were trying to make VR avatars of people, right? Be able to change the view direction. Cool. We validate the efficacy of Control3Diff on standard image generation benchmarks, including FFHQ, AFQ, AFHQ, and ShapeNet. So let's see what FFHQ looks like. FFHQ is flicker faces. Is it 70,000 high-quality PNG images at 1024 by 1024 and considerable variation in terms of age, ethnicity, and image background. So basically a bunch of pictures of people's faces. Only images under permissive licenses were collected, so basically just a huge data set of people faces. And then let's move the paper over here so we can control one and get to that every time. AFHQ, animal faces data set. Okay, so basically the same thing as FFHQ, but instead of people, it's just a bunch of dogs and cats and tigers and lions and bears, probably. And then ShapeNet. ShapeNet, I've seen this one before. ShapeNet dataset is a bunch of 3D models. 3D CAD models developed by Stanford, 300 million models classified into 3,135 classes. So this is obviously a mesh, so the objects in here are going to be stored in meshes, which basically means a collection of 3D points known as vertices, as well as the connections between those. So there you go. Those are, I guess, the 3 data sets that they're going to be using. Thank you for your effort on these papers. I appreciate it, Sahil. Introduction. The synthesis of... Actually, why don't we look at this picture before we move on? So left is the generation process, where diffusion model samples a triplane, which can be used for image rendering. A triplane is just 3 planes. So plane is just one of these flat squares. So a triplane, you can see there's 3 of this. It's starting from some kind of noise. And then optional conditioning. A diffusion model is going to remove that noise, but it's going to remove that noise conditioned on something. Condition just basically means you're giving it a piece of information, and rather than removing noise just kind of however it wants, it's going to remove noise based on that little extra piece of information you've given it. So that can be the text, it can be the edge map, it can be a picture of something, it could be a shape, segmentation map, whatever. Any one of these inputs here are what's going into this conditioning. And you can see how as the diffusion model kind of removes more and more noise, the kind of, I guess, appearance of this person comes out into the triplanes, and then that is fed into what they're calling here a neural renderer, which kind of sounds like a nerf, but it's obviously not a nerf because these do not look like nerfs, but that can generate pictures of this guy's face. Right are the examples of controllable generation given various conditioning inputs showing generated frontal and side views. The faces shown are all generated by models without real identities. That's kind of cool. So this is now the second time I've seen this, probably more times, but more and more for these kind of face papers, the faces that they use in these figures are not real people. So kind of creepy to think about that, like, none of these people are real people. These are all fake generated people. Cool. All right, let's get into the introduction here. The synthesis of photorealistic 3D-aware images of real-world scenes from sparse controlling inputs. Look at all these words. Photorealistic just basically means realistic. 3D-aware. I don't really know what 3D-aware means. 3D-aware doesn't have a formal definition. It's just kind of an image that is aware that, I guess, this guy's face is in front of that hedge, and that this face kind of has a specific 3D kind of shape to it, I guess. Real world scenes just means real world. Sparse controlling inputs. Sparse just means not dense, which basically means limited information. In a long-standing problem in both computer vision, computer graphics, various applications, including robotic simulation, gaming, and virtual reality. There you go. They're dropping that VR. Depending on the task, sparse inputs can be single-view images, guiding poses, or text instructions. There's no poses here. They have a segmentation map, and then they have this mesh of a head, but they don't have any face poses. So media pipe face pose. This is what a face pose looks like. It's basically an agreed upon set of points that represent basically the shape of someone's face, and kind of they're used for face tracking, but we don't see any of that here. We don't see that being used as a control input. The objective is to recover 3D representations and synthesize consistent images from novel view points. This is a challenging problem as the sparse inputs typically contain insufficient information to predict complete 3D details. Consequently, the selection of an appropriate prior during controllable generation is crucial for resolving uncertainties. And 99% of machine learning research is basically this sentence here, is selecting the appropriate prior, right? It's just picking the right thing to look at, the right assumptions to make about the underlying data distribution. Recently, significant progress has been made in the field of 2D image generation through the use of diffusion-based generative models, which learn the prior and have achieved remarkable success in various conditional applications, such as super resolution in painting, image translation, text-guided synthesis. It is natural to consider applying similar approaches in 3D generation. Typically relies heavily on the availability of ground truth data, which is not commonly available for 3D content, especially for single-view images. Yeah, so these data sets that they're using here, this FFHQ, like these have no 3D to them, right? AFHQ, also no 3D. You have a 2D image of this person's face, but you have no idea what the underlying 3D mesh would be for the shape of this face. To address this limitation, we propose a framework called Control3Diff. Links diffusion models to generative adversarial networks take advantage of the success of GANs in 3D-aware image synthesis. Here's a bunch of papers on 3D-aware GANs, I guess. The core idea behind 3D GANs is to learn a generator based on neural fields that fuse. Here's your neural radiance field. Learn a generator based on neural radiance fields that fuse a 3D inductive bias in modeling with volume rendering. So I guess the 3D bias is probably going to be the triplane. Right? Maybe that's the whole bias, but let's see. With random noises and viewpoints as inputs, we can avoid the need for 3D ground truth. Our proposed framework predicts the internal states of a 3D GAN given any conditioning inputs by modeling the prior distribution of the underlying manifolds of real data using diffusion models. Modeling the prior distribution just basically means building a statistical model of the distribution over time, right? That's the whole point of a learning process, is you're building this model of a distribution, usually the data distribution. Underlying manifolds of real data using diffusion models. Furthermore, the proposed framework can be trained on synthetic generation from a 3D GAN, following for infinite examples to be used for training without worrying about overfitting. I mean, I don't know about, you're always going to overfit, so I don't know if this statement holds true for actual infinity. 2D diffusion models were able to learn 3D controllable generation with a single loss function for all conditional tasks. See what this is, probably some kind of reconstruction loss, if I had to guess. This eliminates the use of ad hoc supervisions and constraints which were commonly needed in existing conditional 3D generation. So kind of what they're talking about here is that in a lot of these papers where you're trying to do anything with 3D, 2D to 3D, anything like that, you end up having a lot of complicated loss functions, a lot of constraints, maybe multi-part constraints. We're constraining on one thing and then running an optimization process and then constraining with a different thing and running an optimization process. So kind of getting rid of these complicated loss functions and constraints is a good thing. To validate the proposed framework, we use a variant of the recently proposed EG3D that learns an efficient triplane representation as the basis for Control3Diff. I don't think 3D inductive bias is the triplane. Yeah, there might be a different inductive bias. We extensively conduct experiments on 6 types of inputs and demonstrate the effectiveness on standard benchmarks. Preliminaries. All right, so here's where they're going to explain to us all the different components that are part of their system. Obviously, their system is made of a bunch of different things, and for us to understand the full system, we need to understand the parts, and that's what this section does, right? This preliminaries part. So the first thing that they're going to try to explain here is, let's see, controllable image synthesis in 2D and 3D aware manners, and review the 2D solutions with diffusion models. Then we pose the difficulties of applying similar methods to 3D. 2D, the goal of controllable synthesis is to learn a generative model that synthesizes diverse 2D images X. So there's your first math definition. You have an image X, 2D image, 3-channel 2D image probably. And then you have some input control signal C. This can be mainly done by sampling images in the following ways. you have theta is the parameters of your generative model. So you have some generative model theta here, which samples X conditioned on C. The former one is called guidance. What do I mean by the former one? At test time, the energy function L is used to measure the alignment. So you have some energy function which takes in the C, which is the control signal, and X, which is the image, and measures the alignment between the synthesized image X and the input C to guide the prior generation P of theta. So this is the actual model, right? This is your prior that you're trying to build up over time. And here your X is actually, here's the actual sampling. So this is sampled from. It generally has to do with the domain-specific architectures, especially in GANs. So you're saying that the 3D inductive bias is in the GAN architecture itself, much like the 2D bias of translation and variance is just fundamentally part of the convolutional neural net. Note that for only controllable tasks where the energy function can be defined, the guidance techniques can be applied. Only for controllable tasks where the energy function can be defined. The latter one directly formulates it as a conditional generation problem if the paired data is available. As C typically contains less information than X, it is crucial to handle uncertainties with generative model. Okay, so here they're talking about paired data, and what that means is that for every image X, you're going to have a corresponding conditioning signal C, which basically means that you have this image here, and then you're going to have the C that corresponds to that image, right? So the segmentation map corresponds to this image, this face mesh thing, it corresponds to this image, and so on. But, you know, that's also, you know, they talk about here, oh, we don't need supervision, but the conditioning signal requires that supervision, right? Without any auxiliary supervision. So, I mean, you tell me, is knowing for a fact that this edge map corresponds to this face, is that auxiliary supervision? I feel like kind of is, right? As C typically contains less information, blah, blah, blah. Okay. The above formulation can be simply extended to 3D. In this work, we assume a 3D scene represented by latent representation Z. So there's some latent vector Z, which represents a 3D scene. And we synthesize 3D consistent images by rendering X from RZ pi, given different camera poses pi. So they have some camera pose pi, probably couple different ways. There's a lot of different ways to think about camera poses. In the NERF paper, for example, they think about it as a view angle and a ray, but that kind of ignores the position of the camera. That's just kind of a view direction and a view, like where you're looking from. But if you want to fully define a camera, you need 6 numbers, right? You need the actual XYZ position, and then you need the 3 numbers to specify the exact look direction. So we'll see which one of those they decide to do. We do not restrict the space of Z, meaning that it can be any high-dimensional structure that describes the 3D scene. Okay, so there's no constraints on this latent Z, which is going to represent the 3D scene. We can define a 3D-aware controllable image synthesis by replacing X with Z. Okay, so basically what they're saying is here, your P theta is generating this X, which is a 2D image conditioned on C, and then they're saying, okay, if you just replace the X with the Z, so you just put the Z right here, now you have P theta Z conditioned on C, you can generate this Z, which is the 3D scene, or really just a 3D face, and it's going to be conditioned on this C. Nadi G8YTH, hello bro, how's it going? Diffusion models, let's see how these guys summarize diffusion models. Standard diffusion models are explicitly generative models defined by a Markovian process. So Markovian process, just basically, anytime you see that word Markov, think about a graph in your head. So just a bunch of little balls with little lines that connect them, and then basically the balls represent states, and you can take actions to go to the next state. And then if you take the same action in the same state, you end up at the next state, right? So it's kind of like a way of describing a process that assumes that the process is kind of always going to be repeatable if you do the same set of things. And I think it's always important to note that this Markov assumption is actually kind of low-key bogus. The real world is not Markovian. It's just we pretend that it is because it makes things easier. That's my spicy take on Markov processes. Given an image X, a diffusion model defines a continuous time-latent variables. Z, T, where T is sampled from 0 to 1, and Z0 equals X. So I think what they're talking about here is that you have, usually when you're doing these diffusion models, you're doing a latent diffusion model, which means that you're performing diffusion or the removal and adding of noise in a latent space. That latent space is generally an encoded version of the image X. Here, they're simply saying that at time equals 0, Z is equal to X. Usually, it would be the case that this Z is the result of some kind of image encoder consuming X and returning a latent version of that image. But over the course of this diffusion process, which is going to go from time step equals T all the way, or from time step equals 0 all the way to 1, you're going to have a bunch of these Z's or X's, right? So let me break out my diffusion model image that I always like to refer to. Where is it? Where's that doggo? Here you go. So here you have a bunch of X's. This is X0 is the actual image, right? Open image in new tab, just so we can delete that. Ugh. And then you can see how at time step T, it's pure noise. Based on a fixed schedule, alpha T, sigma T. So alpha T and sigma T define the actual schedule of how noise is added. You can see here this is a normal distribution. Here, a normal distribution that alpha bar TS, alpha bar is going to depend on T. Do they actually show you that? Damn, they're like packing in all these equations into a paragraph here. It's kind of difficult to read. S is in between 0, T, and 1. The fuck is S? Here we go, latent Z of T. And anytime by QZT condition on Z0 is a normal distribution, ZT, this is the variance here, and this is the mean. The model learns the reverse process by denoising ZT to the clean target with weighted reconstruction loss L theta. So this is the actual schedule of how the noise gets added. And obviously the noise is dependent on T. And then S, I guess, is the steps, which doesn't necessarily need to be T. This is kind of a confusing thing here. I think S and T just both refer to the steps here. But they decide to break it apart because you can change the S, I think. Markov is for proofs and formalizing lies. I agree with that. And all of reinforcement learning is just linchpinned on this Markovian process assumption. If you just, it's like this giant house of cards built upon that Markov assumption. You just get rid of that, it just disappears. So something to think about, that all reinforcement learning is basically a lie. So this is the reconstruction loss that is used to train these diffusion models. Obviously, you have basically the image that you actually want, which is Z theta, and then you have basically the reconstructed image here, and they're taking every single little value. Here it would just be the pixels, but usually in the latent space, you would just be taking the individual parts of that latent image and then doing the L2 difference between them. And here the weighted part of the reconstruction loss means that there's a weight here. So there's specific weights for specific parts of the image. Some things are worth more than others. That's why you use a weighted reconstruction loss. And here you just have the expected value from z of t sampled from this q, which generates a z of t conditioned on z 0 and then t in 0 to 1, or t sampled from 0 to 1. Theta is parameterized as a unit. So generally the diffusion model itself is a unit. Sampling from a learned model p theta can be performed using ancestral sampling rules. What the fuck is that? I've never heard that defined that way. Jonathan Ho, denoising diffusion probabilistic models. They're calling it ancestral sampling. Is that just a meme because it's old school? Starting with a pure Gaussian noise, you have the definition for a pure Gaussian right there, a normal distribution 0 with identity variance. We sample S and T according to a uniformly spaced sequence from 1 to 0. Z of S equals alpha S Z theta ZT plus square root of sigma squared S sigma bar squared epsilon theta. There's a lot of unnecessary fanciness here, but basically they're reparameterizing this equation up here such that you can just plug in a normal distribution here, and you see that makes it easy because now you can pull out this term here and this term here, these epsilons. Right, so it allows you to sample from this, what would be kind of a complicated distribution here, this normal that they define up here, and it becomes really easy. Now all you have to do is just sample from a normal distribution that you can just define pretty easily in any mathematical programming package, and then multiply it by these sigma and sigma bar and alpha terms and get the actual value that you want. Decomposing this sophisticated generative process into hundreds of denoising steps. That's why diffusion models are so slow. Diffusion models effectively expand the modeling capacity and have been shown to have superior performance than other types of generative models. For even better efficiency, latent diffusion models, which is kind of what I've been describing, are extended the process by using the latent space by basically having this encoder, which is generally not trained as part of the diffusion training process, right? Generally, these image encoders are trained entirely separately via some VAE on a massive data set. Due to the autoregressive nature, diffusion models are suitable for controllable generation. Prior research studied guidance with a variety of classifiers, constraints, or auxiliary loss functions. So guidance is just what you're controlling the generation with, right? So guidance is what are you choosing for this C here? And this C can be anything. It can be a combination of anything. So it can be this seg map. It can be the seg map and an edge map. It can just be text. It can be text and whatever this mesh is. It can be whatever you want, or any combination of whatever you want. So the hard part is not picking what you want to guide it with, but finding a data set where you have a kind of matching one-to-one pairing of like, here's the image and then here's the conditioning or guidance that is used for that image. Right, the harder part is getting the data set. AS is just a way of calling on the Markov chain process in diffusion. Other works explored learning conditional diffusion models with parallel data, class labels, text prompts, align image maps. More importantly, classifier-free guidance, which enables generation with a balance between sampling controlled quality and diversity, has become a basic building block for large-scale diffusion models. Okay, so that's their definition of diffusion models. I feel like that's pretty standard. I don't like this like fucking jarble of equations inside the paragraph like that. I feel like they could have separated it out, but other than that, pretty good. Comparisons between reconstruction-based and GAN-based approaches for obtaining latents for the learning of the latent diffusion model. Kind of an interesting, they have an arrow representing the first part of this figure, so everything above this line, and then an arrow representing the bottom part of this figure, everything below this line. Learned samples from autodecoders generally have lower quality than 3D GANs due to regularization and optimization difficulties. So what do they mean here? So you have an image here. You're encoding it into some z and some pi, where pi is the camera pose, and then z is the latent representation of the 3D scene. So this z actually tells you that this is a cat, and then the pi tells you where is the image of the cat taken from. We don't really know what R is, but some kind of decoder, right, that reconstructs the original image, or attempts to reconstruct the original image from this z and this pi. And here you have the reconstructed image. You can see it's a little bit blurrier, not quite the same as the original image, and then you could use some kind of reconstruction loss and then push those gradients, and then in that way train this R. Likely collapsed unless heavily regularized. So they're saying that this z here, you could have some prior constraints on it. So you could have some constraints on the z such that it follows a specific shape or has some specific properties to it. And then here they have 3D GAN. So this G probably represents the generator in a GAN. The generator is starting from noise and is generating some Z, and that Z, in combination with a noisy, some kind of random camera pose, so you're starting from a random, or a generated Z, which represents the actual 3D object, and then a pi, which is just some random camera position. Feed that into this same R here, which is generating the actual image, and you get the image. And here, this real or fake, this is unlike a reconstruction loss, right? With a reconstruction loss, the gradients that you push are basically the difference between these two images. But when you're training a generative adversarial network, your loss is coming from a discriminator, which is a neural network that is basically making this choice. It's basically saying, is this a real image or a fake image? And when it makes that choice, because of the way that the discriminator is set up, you can basically get the gradients that go all the way back into the generator, such that you know which part of the generator was responsible for generating specific parts of the image, maybe like this little tip of the ear or the part around the eye. So the discriminator is not just giving it a very sparse real and fake signal, it's actually a much denser gradient signal, such that you can make this G better over time. And I guess here they're showing you that 3D GANs are better at generating cat faces than autodecoders. I guess. 3D aware image synthesis. So we're still in the preliminary section here. So when extending image synthesis to 3D, one can model each 3D scene, which corresponds to a latent representation Z. There you go. Z represents the 3D scene as a neural radiance field. All right, here you go. Here's a NERF. So the NERF FZ, what is FZ? R5 to R4 plus maps every spatial point and the viewing direction to its radiance and density. Okay, so what this terminology here is saying is that a neural radiance field, or a NERF, is a function which is mapping. So that's what this arrow is telling you. It's telling you that you're going from the input, which is R5, which is 5 numbers basically, and then it's turning it into R4, which is 4 numbers. But that's a very confusing way of NERF neural net of showing what a NERF is. I much prefer this picture. Actually, let's get this picture. This picture is even better. So a NERF, which is this little f theta here, it's a little neural net, it's a little multi-layer perceptron. What the NERF takes as input is a single point in space, right, x, y, and z, which is this point in space. And then it's also taking this theta and this phi, which represent the view angle of a camera. But note how this is only the view angle. So there's no notion of basically the rotation. So like how much is the camera like rotated? And there's also no notion of the camera position. So it doesn't know where this camera is in 3D space. So as far as a NERF is concerned, this camera could be 1 million miles away, or it could be 1 inch away from this point, and the NERF would actually give you the same exact output. And the output of a NERF is, here you have 4 numbers. You have the red color, the green color, the blue color, and then you also have this sigma here, which represents usually the transparency or the density or the opacity. Different ways to describe that. So that's what a NERF is. It's this function here, which is mapping from these 5 numbers into these 4 numbers. maps every spatial point and viewing direction, those are the 4 numbers, into its radiance and density, which are the 4 numbers. FC is parameterized as a multi-layer perceptron, which is just a very simple little neural net with a couple different layers, or triplanes with upsamplers. So here's, I guess, where they're getting the triplane idea from. Next, we can synthesize 3D consistent images via volume rendering. So NeRFs don't actually give you a final 3D thing that you can see, right? What NeRF gives you is an individual point, and then once you basically sample a bunch of points in a volume, then you can aggregate all of those points together and do this extra step, this actual volume rendering, and this is where you actually get the image, right? This is where you actually get a 2D image which represents the NeRF, but the NeRF itself is not actually rendering anything, right? The NeRF is just representing the shape that is inside of this square, inside this volume. So even with a NeRF, that a NeRF is just a bunch of numbers in a matrix sitting in your computer. And if in order to actually get a 2D image from that, you're going to have to do this extra volume rendering, which usually involves ray marching, which is basically going down, marching along this ray and adding together all these little numbers and then getting a final color, which you end up putting in your image. Danielle Mika joining a bit late. Welcome. Yeah, I think you were the person who recommended this paper, so far so good. So far we're just they just explained diffusion models, and now they're explaining NeRFs. Despite the success in 2D, diffusion models have rarely been applied directly in controllable 3D aware image synthesis with NeRF. This is a huge opportunity, BTW. If you guys are in the research world, diffusion models that are doing diffusion directly in some kind of 3D volume, like, I haven't really seen a super clean, super cool version of that yet. So that's a huge potential research direction. Learning diffusion models requires the 3D ground truth Z, shown in equation 2, that is often unavailable. So this Z here, you don't really have that. There exist approaches to acquire high-quality 3D labels from dense multi-view image collections. For most of these cases, only single-view images are available. And the problem is that these approaches to acquire high-quality 3D labels from dense multi-view image collections, they're not perfect, right? So any kind of 3D from 2D or 3D from collection of 2D images, there's going to be noise introduced into that. So as soon as you start training on things that themselves have noise in it, it can get out of control. So it's no good. It's very difficult to get ground truth for 3D because 3D file formats are just inherently not ground truth, if you want to think of it that way. As discussed in section 2.1, so this fancy little symbol here just means section 2.1, we need an energy function L for guidance or paired data for conditional generation. Okay, so it seems like there's 2 different ways that they're going to be controlling this synthesis. They're either going to be guiding it with this energy function, or they're going to be conditioning the diffusion with some kind of conditioning signal, which is probably just going to be one of these things, right? Either an image or a seg map or an edge map or a text or whatever it is. Both of them are not straightforward to define in the latent space of implicit 3D representations, e.g. a NeRF. Okay. More precisely, targeting on challenge number 1. What is challenge number 1? They didn't really tell us what the fuck challenge number 1 is. Prior arts first recommend the latent Z from a dense multi-view image of each scene. In the rest of this paper, we refer to them as reconstruction-based methods. That is, given a set of posed images, which is already just a terrible assumption, right? So a set of posed image here, so you have the little curly brackets mean a set of things, right? And there's n of these, so you have a set from I equals 1 to capital N. There's n of these images xi, but they're posed, which means that you need to, pi I is the camera of xi. So is this something that you have? Like, if you take a second to think about that, you're never going to know this, right? If I give you a set of images, you can get some approximation for what the camera for the given image xi is, but to actually get the ground truth position of a camera for each image is basically impossible. There's no data set in the world that has perfect ground truth information unless it's synthetic. So these posed images, you're already introducing sloppiness there because the poses are going to have some sloppiness to them. But okay, going beyond that, we have a loss here, RC loss. What is RC? I guess RC stands for reconstruction. Is the expected value of xi sampled from data. So this is just your xi. Here you have the sum of the L2 difference here between r z pi I. What is r? R is the differentiable volume renderer of fz. So r is what actually does the rendering given a nerf fz. So again, the nerf is just what tells you is a field. It's just a function that you can basically evaluate at every single point in some volume. But then in order to actually get the image, right? So here they're doing an L2 loss between the image xi, and you can't, and the image xi can only be compared to another image. So in order to get that image, you basically take the camera pose, you take z, which is the latent or the 3D information, and you, which is in this case a nerf, and then you render it, and then you get an image. So the output of the renderer is an image. You compare that image to the original image. You do the L2 difference between those. You add h. What is h? H is the prior regularization over z. So basically some kind of term that depends on this z here. And there you go, and that's your loss. You want to minimize that. Here, z equals e xi n I equals 1 to n represents either the backward process. So you see here how, much like in a latent diffusion model here, in a latent diffusion model, you're taking the image x and you're encoding it into some latent vector z, which represents that image x, right? And the encoder is something like the encoder part of a variational autoencoder, right? So VAE. I love these VAE neural net. Yeah, so some of these are a little intense, but this is kind of what a VAE is doing, right? A VAE is taking this X, which is an image, then it's got an encoder, compressing it into this latent Z, and then you have a decoder, which is making it back into an image, and these are trained with a reconstruction loss. Actually, this is a better one. So here, the E here is the encoder of a VAE. But the E here is something different, right? So here they're saying Z, which is the 3D Z, right? So Z is, as they're defining it here, the 3D ground truth Z is some kind of encoder which consumes a bunch of images, right? So you can see here how these are different here. Even though they're using the same Z and the same E, which isn't great, I would have used different variables here just to avoid this confusion here, but this E here takes a bunch of images, right? It takes a bunch of these, a set of posed images. Okay, but this encoder represents the backward process of grad ZL recon, also known as auto decoder, that updates Z via SGD or an amortized multi-view encoder. What the fuck? Updates Z. So this makes me think that Z is not a single step. So basically you have to get this Z from a multi-step process that consumes this set of posed images. Let's see, 85. Continuous 3D structure aware neural scene representations. I might have low-key read that. 3D aware neural scene representations. Here we go. Is it this one? I think it's this one. Oh, nope. I want the PDF. Fat fingering. Let's see this. All right, so this is the 3D representation that they're using. Yeah, so this is taking a bunch of, see this, you see how this is like a update? You see how it says depth update? This is making me think that it's like a multi-step process. Initial state update. Oh my god, this is this is hardcore. I'm not going to read all that. But basically, it's some kind of encoder, which is going to take a bunch of these posed images and output some vector z, which represents basically the entire 3D scene. So whatever thing they're using here, we're limited to the quality of that, right? So however good this whatever amortized multi-view encoder is, we're limited to the quality of that. If this amortized multi-view encoder is trash, this entire paper is going to be trash. So they probably want to make that as good as possible. In spite of the good results with dense multi-view data for training, these methods perform poorly when only one view is available for each scene. Challenge 2. I think, Mika, you said challenge 1 is the first point, and then challenge 2 is the second point. So what are the points here? 2, 1, 3D? What am I missing here? Key challenges. All right, I got you. So while there exist, for most cases, only single view images are available. Okay, so they're saying the problem is that you only have one image. You don't have these multiple images, and you certainly don't have multiple images with perfect camera positions. Single view auto decoders usually fail to learn geometry. Even with strong regularization, the reconstructed quality is still limited. On the other side, using on an encoder may ease the aforementioned issues after adopting various auxiliary losses with novel view rendering. Yet, due to limited view coverage and object occlusion, an image encoder is unable to predict fully determined 3D details, resulting in additional uncertainties. We will elaborate on how we address these challenges to achieve controllable 3D aware image synthesis with only single view images for training. I'm not necessarily liking this for other reasons too, right? Because it's like whenever they introduce this at the very beginning of the paper, they talk about like, oh, we're not using priors, we're not using auxiliary supervision, blah, blah, blah. Here's all the... But they are doing that. They're just using it by using an external third-party amortized multi-view encoder that has for sure been trained with a bunch of priors and a bunch of supervision. So you're kind of like outsourcing the dirty work. Okay, method control 3 diff. We present control 3 diff, a controllable 3D aware generation framework based on a 3D GAN. Pipeline is illustrated in figure 3. Instead of acquiring Z from dense multi-view images, XI, as is done in reconstruction-based methods, we directly sample from the learned distribution of Z of a 3D GAN model. Okay, so they're taking some pre-trained 3D GAN model, or no, it's pre-trained but only trained on single view images, and then they're sampling from that. That's kind of weird. Why would the learned distribution of this 3D GAN model, which is trained only on single view images, give you a good latent Z? We build control 3 diff based on EG3D. EG3D first learns a triplane generator. So here's your triplane generator, G. U from R512, Z from 3 by 256 by 256 by 32. Let's actually look at this paper. EG3D, efficient, geometry aware, 3D generative. Efficient, geometry aware, 3D GAN. Yeah, here we go. Actually, wait up, even better. There's a NVIDIA research on it. Accept cookies. High quality multi-view consistent images using only collections of single view 2D photographs. We improve the computational efficiency without overly relying. We do introduce an implicit network architecture, synthesizes not only blah, blah, blah. Okay, so let's actually look at this, though. Are either compute, blah, 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 3D GANs without overly relying. We do introduce an expressive hybrid architecture, synthesizes multi-resolution, decoupling feature generation, and neural rendering. Our framework is able to leverage state-of-the-art 2D CNN generators such as StyleGAN2. Neural implicit representation use fully connected layers, FC, with the positional encoding to represent a scene. Explicit voxel grids or hybrid variants use small implicit decoders. So, I mean, where is the 3D information coming from? You see, here's the triplane. So you have some latent. It's being fed into the generator of this StyleGAN2. So you see the StyleGAN2, you have your discriminator here, and then you have your generator here. Here's you have this triplane. Where are they actually getting the 3D prior for this? We directly optimize the features of the plane and the weights of decoder to views of a scene from the tanks and temples. Boom. There you go. Tanks and temples. Okay, so it seems like this GAN here learns the implicit. Implicit just basically means that the prior is being stored in the weights of the neural net, right? It's not explicit. Explicit would mean that you're explicitly telling it, here's the prior that I want you to use for 3D. Implicit means the prior is within the weights. It's been learned. But kind of what I'm looking for, why I'm looking at this paper, is like, where is this prior coming from, right? At some point, someone put this prior in there, and then now this paper is saying, hey, we just magically get this prior from this Ego EG3D. But I think that prior is coming from somewhere. And I think the prior is coming from this tanks dataset. Right here. 360-degree views of the tanks and temples. Primary advantage, hybrid representation. Okay. But anyways, they're using this triplane based on this EG3D, which maps low-dimensional noises to expressive triplane. The feature of a 3D point is obtained by projecting the point to 3 orthogonal planes and gathering local features. Orthogonal planes just means that they're perpendicular to each other, right? Gathering local features from the 3 planes, which is the input to the radiance function Fz for the radiance and density prediction. Input to the radiance function Fc, which is the nerf. So they're feeding the information of these planes into the nerf. Training an EG3D model requires a joint optimization of a camera condition discriminator D, and we adopt a non-saturating logistic objective with R1 regularization. A joint optimization of a camera condition discriminator D. So joint optimization means you're optimizing multiple things, right? That's where the joint is. You're optimizing one thing and another thing at the same time, and those two things might have different objectives. We adopt a non-saturating logistic objective with an R1 regularization. So the loss that you're using to train this GAN has two terms. It has this first term here. So you're trying to minimize two things at the same time. This first thing here, E, where you have U sampled from a normal. So you have U, which is just some number sampled from a normal distribution. Here you have pi sampled from the set of all camera positions, prior camera distribution. So, I mean, this just makes it sound fancy, but like pi is just a camera pose, and then pi here is sampled from the prior camera distribution. So there's some distribution of all camera poses, and that's what they mean here with this capital pi here. And then you have like 10 functions applied on each other. So you have the camera pose, and then you have H. H consumes the camera pose and then whatever this is, which is the discriminator. The discriminator consumes the camera pose and then whatever this is, which is the generator, or the rendering, neural rendering. The neural rendering consumes the G. So I'm going to unpack this because this is a lot of different things inside of things. So the U is noise. The noise is used to generate with the generator part of the GAN here. Then the generator part of the GAN, along with the camera pose, is used with the actual rendering, which is this R function, to create an image. That image is given to the discriminator D, which this ends here. And then the output of the discriminator, which is the real or fake, is used along with the camera pose into this H, which I think is the energy function. Is that what the H was? Did they define this H? Lowercase h? Did I miss it? Same page? This is the same H here. Define next. Oh, I'm fucking stupid. It's right here. H equals negative log of 1 plus the exponent of negative u. Why is H dependent on pi then? Right? That's kind of weird. If H is a function that only depends on u, then why are you doing comma pi here? Right? All right. I think it's because they're missing an open bracket. You see there's a typo here. There's 1 bracket, 2 open brackets, 3 open brackets, 4 open brackets, but then here they only have 1 closed bracket, another closed bracket, and then a third one. So they're missing 1 closed bracket. You see there's a typo in this equation. This pi, the camera pose, is used by the discriminator. The discriminator has access to the camera pose, but this H, of which there should be a bracket right there, does not use the camera pose. It only is a function of u. Yeah. So there you go. We're finding mistakes in these papers because no one else fucking reads these papers, is what we're learning. Not even the people who write them. Okay, but what else? So that's the first term in this loss function. The second term in this loss function takes x, which is the original image, and then it takes pi from the data, so I guess from your set of posed images. And it does the same H of negative discriminator of x and pi, and then here you have a gamma, which is probably some hyperparameter of the discriminator x pi squared. The adversarial learning enables the training on single view images as it only forces the model output to match the training data distribution rather than learn a one-to-one mapping as an autoencoder. Note that in order to train diffusion models more stable besides equation 5, we also bound GU with tan H and apply an additional L2 loss similar to when training EG3D. So they have a constraint on the generator. However, we observed in our experiments that these additional constraints would not affect the performance. Okay, so they're not going to constrain the generator. After EG3D is trained, as the second stage, we apply the denoising on the triplane to train a diffusion model with the renderer R frozen. The renderer is a neural, is just a, you're not freezing it. The volume rendering is not a neural net. The volume rendering is just a process. Training follows the same denoising objective, and Z theta equals generator of U. U is randomly sampled, and we can essentially learn from unlimited data. So, okay, so what do they mean by this? So, let's go to our picture of a, not a diffusion. Did we have a picture of a generative adversarial network somewhere here? GAN. Generative adversarial network. So the generator consumes, that's a terrible pick, but it consumes this vector U, which is just noise, right? And what does that mean? It means that you can give, once you train a generator, you can basically give it any vector U. Can't fucking find a picture here. Here's a picture. So the generator is taking some input here, which is this U, right? And then it's generating an image. But you can give any, so you train it with some things, but then you can basically just randomly pick a random U here, and it'll generate a picture, right? So that's what they're saying. They're saying that we can put in any U here, which is sampled from a normal distribution, and get an image for free, basically. But I would argue this is not unlimited data. Your generator here is not going to generate unlimited data because there is some underlying data distribution which it has learned to model. So if you sampled 10 billion U's and then fed them through the generator and got a bunch of these Z's, it wouldn't technically be an infinite number of Z's, right? Like a bunch of those Z's would actually be the same way that like if you generated if you picked the vector that generates this picture of a mandrill, right, which is a monkey, and there's some area around that initial vector that goes in that'll generate basically the same picture of the mandrill, and so on. So like the space that is being used to generate these images is not infinite resolution, right? It's kind of like it's limited to whatever the original data distribution that you use to train that GAN is. So I don't know, I disagree with this unlimited data because the data that you're going to generate is going to be limited by what you were originally used to train this GAN. I think their notation assumes the renderer includes a few layers to transform this features from the triplane into the nerf like output for volume rendering. Yeah, I think what they meant is that the nerf itself is frozen. They're not fucking with the nerf. Different from 60, we do not any auxiliary loss or additional architectural change. Optionally, we can add the control signal as the conditioning to the diffusion network to formulate a conditional generation framework for controlling. Okay. We note that training a diffusion model over GU samples differs from distilling a pre-trained GAN into another GAN generator, which is unsuitable for controlling tasks. Training a diffusion model over GU samples differs from distilling a pre-trained GAN into another GAN generator. So they're saying if I pick random values for you, feed them into this generator, and generate a bunch of images which correspond to that, or in this case they're not images, in this case they're 3D latents, so some kind of scene, 3D scene represented in a latent vector Z. That's different from distilling this pre-trained GAN into a different GAN. Kind of, yes, sure. This is not a, there you go. Although it is efficient to sample high-quality triplanes Z, GANs are implicit generative models and do not model the likelihood of the learned latent space. That is to say, we do not have a proper prior given the latent representations of a 3D GAN. We don't really know what the distribution over this Z is, right? Especially in the high-dimensional spaces like triplanes, any control without knowing the underlying density will easily fall off the learned manifold and output degenerated results. What do they mean by this? In a high-dimensional space like triplanes, okay, so I have a triplane. In my head, I'm imagining this triplane. Any control without knowing the underlying density will fall off the learned manifold. So the learned manifold is the part of this P of Z that we've learned, or that actually exists, right? The learned latent space. Some parts of that are like pretty well defined because our data set maps to them, and other parts of that are not well defined. And if you end up in a part of that learned manifold that is outside of the area that you trained on and that you shaped with your training, then you're basically just going to generate a bunch of noise. As a result, almost all existing works utilize 3D GANs for controlling the focus on low-dimensional spaces, which can be approximately assumed as Gaussian. However, this has to sacrifice, I think is what they meant, the controllability. In contrast, diffusion models explicitly learn the score functions of the latent distribution even with high dimensionality. Which fills the missing piece for 3D GANs. This is very dense. Like, there's so much here to think about. Give me a second. I need more caffeine. After a point in time, it's just too many words meaning the same thing. I think that they mean if you try to do any guidance or conditioning on triplanes, you get back noise. Yeah. Yeah, so I mean, there's kind of a fundamental intuition here where basically anytime you're learning, using a learning process and you're learning this latent space, right? You're basically shaping that latent space. That only works in interpolation, right? So the latent space of this GAN, which has been trained on basically, or this one here, right, which has been trained entirely on faces, I guess this one here, not any of those, it can only interpolate other faces. If you try to access a part of this latent space that is not a face, you're going to be extrapolating outside of the distribution, outside of this learned manifold, and therefore you cannot expect that to be anything reasonable. It's just going to be basically a bunch of noise, which kind of fits for like, I think like in my head, I generally always like think about like curve fitting, you know, where it's like, ultimately, when you're learning this latent space, you're shaping it, but you're only shaping it in the area where you have data, right? If you could think of this as like, this is pictures of people's faces, and then we learn this latent space, which says, okay, well, here you have this face and this face. I can show you what this face looks like, right? The face that's kind of in between these two faces. But if I go and I say, okay, well, what's a car? And maybe that's a point all the way over here. That's our latent space, our manifold here that we've learned no longer has it is no longer going to give you a good point to represent that object. I don't know what they mean by this low dimensional can be appropriately assumed as Gaussian thing. Because I feel like the Gaussian assumption isn't constrained to the dimensionality of what you're trying to model. I don't know. I feel like I'm still missing a piece of intuition here, but let's keep going because or else the stream's going to be too long. Bro, is there any model that can do automatically UV map and create textures? Probably. I feel like that has to exist. I've seen that. Diffusion. Diffusion for 3D model textures. Here you go. There's already a Blender plugin for it. Stable Diffusion 3D plugin. That's not going to do the UV mapping. UV mapping is more complicated, right? Texture is just a PNG, but then the UV mapping is like how do you wrap that texture around a mesh? So I don't know if people can do that automatically. Now that we've read that, let's look at their actual pipeline. So figure 3 pipeline, a 3D GAN training. Diffusion model trained on the extracted triplanes can be trained with or without the input conditioning. This is part A. So we have U, which is some randomly sampled U sampled from 0i. That's fed into the generator. The generator is going to create this Z, which is a triplane, which they're calling their high dimensional latent. That high dimensional latent is fed into this R, which is the rendering function here, but R is really composed of a couple different things. It's basically volume rendering and then a nerf, where the nerf weights are frozen. That's going to generate an image. That image is basically going to be classified by the discriminator as either real or fake. Okay. So basically it's a generative, it's a GAN, but rather than the GAN generating an image, a 2D image, what the GAN is generating is it's generating this triplane Z, and that Z is being used along with a nerf to generate a 2D image. So that TLDR, that's pretty much all this says. Okay, B. Diffusion model trained on the extracted triplanes can be trained with or without the input conditioning. So now you are in part B here. You have this triplane representation. The denoiser, right? The UNet in Stable Diffusion, what it's denoising, what it's adding noise to and removing the noise from, is this triplane representation, right? And all you need to go from one time step to the next time step in this diffusion process is you need E, which is just your normal Gaussian here, right? E sampled from N0i, and some time step T, and that'll give you the Z at time step T, the 3D latent at time step T. And then what is this optional? So this is the conditioning. So you're conditioning the denoising process, and you're conditioning it on this 2D image going through an image encoder. Input conditioning. I would have thought that the input conditioning is... This is the segmentation, right? So this is I don't think this is a good image. I think this should be the segmentation image or the text or the edge map or something like that. That's what's actually being used here to conditionally guide this diffusion process. And then part C, controllable 3D generation with a learned diffusion model, optionally with guidance. Conditioning, you're feeding this image into an encoder that's being used by the denoiser to condition the diffusion of this triplane Z latent. That triplane Z latent is fed into this nerf, which can render it into a 2D image. That 2D image that it renders, which is this kind of weird, shitty looking cat here, is fed into this loss function here. That loss function allows you to push gradients through this renderer, but note that this render is frozen. So we're not actually modifying the nerf here at all. Those gradients are going into the actual denoiser part here. And over time, this denoiser is going to get better and better and better. Camera poses are omitted for better visual convenience. Yeah, so what they mean by that is that this discriminator is also taking in camera pose pi, and the renderer R is also taking camera pose pi. So for every single image, there's also some camera pose, and that camera pose is coming into here, into this renderer, and it's also coming into here, this discriminator. And that's kind of one of the things I don't like is that that camera pose is not real. Like you don't, like that person screaming at the airplane, that person's not real. The camera pose is not real. We're pretending that camera pose is ground truth when we know for a fact it's not. Okay, conditional 3D diffusion. We can synthesize controllable images by extending latent diffusion to a conditional generation framework. Conventionally, learning such conditional models requires labeling parallel corpus, i.e., large-scale text-image pairs for the text-image task. Compared to acquiring 2D paired data, creating a paired data of the control signal and 3D representation is much more difficult. In our method, however, we can easily synthesize an infinite number of pairs of the control signal and triplanes by using the rendered images of the triplane from a 3D GAN to predict the control signal. But yeah, I just don't like this, right? Because you can't actually generate an infinite number of pairs. The GAN has some limited capacity, right? The GAN was trained on some original data set, and at some point, it's limited to the size of that data set that it was trained on. It's not like you can just ask this GAN to generate anything. It's going to generate up to the point at which it was trained on. Now the learning objective can be written as follows. So here's your conditional loss. Your conditional loss is the expectation for Z0, which is the original image. In a latent diffusion model, it would be the original latent image, and in this model, it's the original triplane latent. ZT, which is basically pure noise, triplane latent. T, which is the time step, and then pi, which is the camera angle. You have WT, these are weights. It's a weighted learning objective here, and you're subtracting the original triplane latent, or what they're calling the sampled triplane. And then here's the rendered triplane at that point. Off-the-shelf prediction module that converts rendered images into C. Edge detector for edge map. So A is a function which takes your image, which is this image of Einstein, or this image of this person, or this image of this guy, and creates this. So this is also introducing errors. So not only do you have errors in that camera pose, but you also have errors in this function A, right? Because this function A, which is a segmentation model or an edge detection model, there's an error there as well, right? Because this edge map is not going to be perfect. This edge map's not going to be perfect. The segmentation map's not going to be perfect. So that function A is also introducing errors, this A here. And pi, sampled from pi, is a predefined camera distribution based on the testing preference. Okay, Z theta represents a conditional denoiser that learns to predict the denoised triplanes given the condition. Okay, so that's just the UNet in the diffusion model. In early exploration, we noticed that the prior camera distribution pi significantly impacts the generalizability of the learned model. So what do you know? If you try to extrapolate beyond that camera distribution, you run into a bunch of issues, which we probably could have guessed. Where for some data sets, the biased camera distribution, and most cameras distributions are going to be biased, right? There's kind of generally this object-centric bias, and then any data set that has camera poses is also going to be biased to some specific thing, usually frontal shots, head shots, the like kind of three-quarter shot. Therefore, we specifically resample the cameras for these data sets. How the fuck do you resample the camera? Joint diffusion with camera pose, pi C. Conditional models can be learned without camera input, which implicitly maps the input view to the global triplane space. It implies that conditional models can predict camera information through diffusion. This seems like you're opening a can of worms here that you don't want to be opening. In light of this observation, we propose to jointly predict the input camera pose pi C with Z in one diffusion framework. Similar to 3D aware generation, predicting cameras from a single view is also a challenging problem requiring resolving ambiguities in a natural image. Yeah, not only is it a challenging problem, but like it's introducing error in a different way now, because now you're predicting this pi c. So now it's not only does it have potentially measurement uncertainty, but now you actually have the prediction uncertainty as well. Previous works rely on external deterministic camera predictors or optimize the cameras at inference time. We flatten pi c into a vector, broadcast it, and then concatenate it into the channels of z as the new diffusion target. Okay, so this diffusion model, the camera pose is like baked into this c, is basically what's happening. They're broadcasting it and concatenating it into the channels of z. Anytime you see broadcast like that, that's generally not great, because it means they're wasting a bunch of memory. That means they're putting it in. They're basically duplicating this pi c multiple points. So you're wasting a bunch of matmols, or wasting a bunch of memory. Guided 3D diffusion. An alternative way to control image synthesis is to follow a similar recipe in 2D to perform test time guidance based on a task-specific energy function, this L, which is task-specific. Nevertheless, directly defining such an energy function between C and a 3D representation is challenging. We circumvent this by defining the energy function to measure the closeness between C and the differentiably rendered image R. How are you going to measure the closeness between an edge map and an image, or a text in an image? We can learn the 3D representation using a 2D rendering guidance, e.g. clip score. There you go. So the energy function is basically how far off does clip think that the image that you've generated is to the image that was used to generate this Z. Fucking clip is coming back everywhere. For text to 3D and MSC or perceptual loss for image inversion. Using 2D guidance for learning 3D representation is reasonable, since the final targets of most controlling tasks we care about are images synthesized from certain viewpoints. 2D rendering guidance can be implemented via efficient remap replacing of z theta zt with z hat theta zt as this. So z hat theta, z theta is the denoised triplane derived from the unconditional prior. Okay, so this is the classifier free guidance that they're doing, right? So their classifier free guidance is a technique in diffusion models where you generate, or you remove the noise conditioned on something, and then you remove the noise not conditioned on this something, right? So you're removing the noise conditioned on the text, which can be like, this is a cat, and then you remove the noise but not conditioned on the text, this is a cat. And then you can look at the difference between those. And that's what they're doing here. So derived from the unconditioned prior. So this is unconditioned. Here you have conditioned, right? So z theta zt, but conditioned on this camera pose, and then conditioned on this C, or not conditioned on that C, conditioned on the camera pose for this rendering, but then you get an image, and then you take that image along with this conditioning vector, you put it into this energy function, which is basically a clip score. Where is this W? Time-dependent weight. So now you have an additional hyperparameter that changes depending on the time along the diffusion process. That's going to be so annoying. How are they going to get this W? Oh my god, they're just introducing more crap. Langevin correction steps. While the 2D rendering guidance can provide a gradient to learning 3D representations, the optimization is not often stable due to the nonlinearity of mapping from 2D to 3D. Our initial experiments show that every early guidance steps get stuck in a local minimum with incorrect geometry prediction, which is hard to correct in the later denoising stage when the noise level decreases. Okay, so in this multi-step diffusion process, you're starting from pure noise, and then you're removing this noise. And that initially, some of those first steps they get stuck in this local minima, and then once they get stuck in that local minima, because the noise is removed based on this ZT, right? Z theta takes as input ZT. As if your ZT is crap and stuck in this local minimum, then your Z theta is going to start to be crap, right? Which is hard to correct later. Therefore, we adopt ideas from the predictor corrector to include additional Langevin correction steps. So when I see Langevin, I just think Brownian motion in my head, but this is like archaic shit here. According to Langevin Monte Carlo, one of these is Monte Carlo. MCMC. Langevin MCMC. Monte Carlo, Langevin Monte Carlo, Markov chain Monte Carlo. That's what the MCMC means. Obtaining random samples, LCMC is also known as the Metropolis Adjusted Langevin Algorithm, MALA. The method generates sequences of random observations when direct sampling is difficult. A visualization of sampling using Langevin dynamics. Langevin Monte Carlo is a class of Markov multi-chain algorithms that generates samples from a probability distribution of interest by simulating the Langevin equation. Yeah, there we go. There's the Brownian motion. Okay, I knew that my brain stored Brownian motion and Langevin together at the same place for a reason. So it's almost like I want to say this is like a Kalman filter, right? You have the actual term, and then you have this noise term, and then you have two terms for each of distributed according to some probability density function, also distributed according to P infinity. Okay, so what are they doing with this? So you have epsilon prime sampled from the normal. You have some delta step size, which I think refers to the step size of this kind of Brownian motion sampling technique, I guess. Like, what is the size of these steps that you're taking? And then sigma t is the time-dependent term or schedule, right? So sigma t changes according to what time step you're at. But we're kind of getting too deep here. Ultimately, what the hell is this ZT? It's basically the ZT is just the triplane latent, and all you're doing is you're just adding this weird extra term here that depends on another hyperparameter called this delta, which is itself part of this Langevin Markov chain Monte Carlo process. Which helps ZT match the distribution. Okay, so basically they're doing a bunch of fancy math here to adjust for the fact that the process of denoising this triplane can get stuck in local minima, and because the triplane is representing some 3D geometry, if you get it wrong at the very beginning, it completely fucks the rest of the denoising process. So you have to get it right at the beginning, which is the whole reason they're doing this Langevin correction. Okay, kind of makes sense in my head, but to be honest, this is very hardcore. All right, let's get this. Discussion, conditioning versus guidance. Compared to guidance methods in section 3.3, training a conditional 3D diffusion model has several benefits. First, in a guided diffusion, a proper designed differentiable energy function is necessary to backpropagate the gradient guidance to the diffusion model, which, however, is not available for all kinds of conditional tasks. Conditional models don't have such requirements, can adapt any conditional distribution. Conditioning is computationally more efficient because the guidance requires rendering and backpropagating through a volume renderer at each step. However, conditioning methods might have a possible issue. As we train our models based on the images generated by a pre-trained 3D GAN, the learned PZ condition on C probably has domain gaps between real images and synthesized images. Yeah, so again, because they're using this pre-trained 3D GAN, that pre-trained 3D GAN is really only valid for generating images within the distribution of images that it was trained on. And especially if you just start picking random U's and then feeding those through the GAN and getting random triplane latent Z, if you drift too far away from the distribution of the original images or the original triplane Z's that are supposed to come out of this 3D GAN, you're just going to start getting a bunch of nonsense. And the real and the fake images are going to be worse. The distance between those is going to be worse. We combine the best of both worlds when L is available. We learn a conditional diffusion model and generate samples jointly with guidance. So generating the samples with the conditioning, without the conditioning, and then you can trade off between those. Can also be used when the test camera is not given. The guidance is used to update the camera pi C predicted by aforementioned conditional model. Yeah, and then here they talk again about the fact that, okay, you don't technically need this pi C, but that pi C has to be kind of limited to this camera distribution, capital Pi here, right? So sure, you can generate it without a known pi C, but that pi C better be really close or within pi capital here, this predefined camera distribution, because if you wander outside of this predefined camera distribution, this pi C is going to be trash, and then that pi C being trash is going to just basically propagate everywhere, and your entire thing is going to be trash. So you're limited to the kind of set of camera angles where this 3D GAN was trained. So basically all their constraints are basically implicit. So they're soft and they're hidden. We evaluate Control 3 Diff on 3 standard image generation benchmarks: FFHQ, just 512, AFHQ 512, and ShapeNet 128. So this is just the image size. So they're actually reducing the size here, right? Because actually it seems like FFHQ is 1024 by 1024. So they're making them smaller here, 512 by 512. And ShapeNet, which we learned has over 3,000 classes, they're limiting it to cars and chairs. It seems like a very small subset. Each image is associated with this camera pose. We consider 6 controllable 3D aware generation tasks. We test the standard image to 3D, edge map to 3D. For faces, we further explore segmentation to 3D, head shape, blah, 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 compare with previous works, seg to 3D, and we additionally train one model in Celeb A HQ. Does Celeb A HQ have image or camera poses? I think you can probably assume a camera pose, but we choose a standard optimization-based and encoder-based approach for the image to 3D inversion and the recent Pix to Pix 3D as the major baseline. Our model fine-tuning without the model weights. Okay, for image synthesis quality, we report 5 standard metrics: PSNR, peak signal to noise ratio, SSIM, I think this is the inception net distance, or is that LPIPS? Frichet inception distance, KID, SG diversity, all of these are, some of these are basically distances in the embedding space of a image encoder, like a inception convnet, and some of these are more classic, kind of like this PSNR, but all of these I generally tend to be somewhat skeptical of because I don't think they capture the true semantic similarity Even though this is literally, I think this SSIM stands for semantic similarity. Yeah, no, structural similarity index, okay. Structural similarity is based on hypersphere distance, perceived quality of digital television and cinematic pictures. For faces, we computed the cosine similarity of facial embeddings generated by the facial recognition network for the given pair of faces. In the context of conditional generation tasks, we evaluate methods using mean intersection over union and mean pixel accuracy for segmentation maps. What am I looking at here? Pix-to-Pix 3D. So you're inputting this. This is being used to control the diffusion, whereas the same U, which is the vector that goes into the generator that generates the triplanes, is being used for these. So this should be the same camera pose basically. And I guess their technique kind of works better. It like makes the face, but I feel like they should have. It's difficult to compare because the people are just different. All faces are model generated and not real identities. You got cars, you got chairs, you got cats, you got humans. This one's pretty good. Quantitative comparison of seg to face and seg to cat. So this is where they're looking at the mean intersection over union of the segmentation maps for the cat faces and the human faces. And then they're comparing to P2P 3D, which is this Pix-to-Pix 3D here. Kind of seems like these numbers are close, 0.67, 0.64, 0.79, 0.76. Seems like this technique does a little bit better on faces, but that could also be because these metrics are better defined on faces. You know, much like we have an easier time telling human faces apart, I bet you Inception Net that is used in this FID also has a better time telling apart faces, or an easier time telling apart faces. What else? We skipped some of these here. Comparison of 3D inverted in the wild images. We compare the proposed approach to direct prediction of the GAN's latent W and triplane with a learned encoder, as well as optimization-based approach to infer the latent and expanded latent W plus, as well as the triplane. Our method achieves better view consistency with a higher output image quality compared to baselines. Predicted W, predicted triplane, optimized W plus, optimized triplane. So I think here they're talking about how their triplane is the result of this optimization process, this joint optimization process. And they said that another way to do this would just be to just predict the triplane directly, right? Train an encoder-decoder that predicts the triplane given an image. And obviously this does seem better. And here they're saying, oh, look at this. Without the camera pose, you can actually get pretty much the same thing. But I think the without camera is misleading because the camera distribution is so similar for every single one of these. You know, it's like the camera, the difference in the camera position is very tiny. It's like in pretty much every single image that has been trained on, the camera position is like almost identical every single time. So being able to do it without the camera isn't that impressive. And then this is the table for this. So numerical, quantitative metrics, and then here subjective comparison, qualitative comparison. There's like weird artifacts that come from this opt triplane here. Image to 3D inversion. We evaluate control 3diff on 3D inversion tasks, comparing our methods to two cases, standard inversion and more challenging 3D super resolution. We directly optimize the low-dimensional latent vectors W and W+, following 2, as well as triplanes. As conventional GANs do not have a learned priors in these spaces, optimization is performed with noise injection regularization. So some kind of regularization technique where you inject noise and it should be robust to that noise. We employ an encoder-based approach that directly predicts the triplanes. To predict triplanes, we train a separate encoder. So they train a separate encoder that basically says, here's the image. I want to predict the triplanes, and then you have a decoder that says, here's the triplanes. I'm going to predict the image, and then you reconstruction loss the original image fed into this triplane encoder, and then the output of the triplane decoder, where methods significantly outperform other methods in terms of both image quality and identity consistency. Visual comparisons. For 3D super resolution, we evaluate our methods on more general conditional 3D generation tasks where the input control is not necessarily the target view. Segmentation ground truth is obtained via clustering the Dino feature. So Dino is a image encoder that comes out of Meta. It has been observed that this clustering adversely affects the performance of cat parsing networks. What the fuck is a cat parsing network? Results of our evaluation presented in table 2. Text to 3D synthesis. So here they're conditioning the denoising of the triplane latent with text, and here's the text that they're using, a middle-aged woman with curly brown hair and pink lips, and that's what you get. And then a middle-aged man with a receding hairline, a thick beard, and hazel eyes. I feel like that kind of works. This Joker is particularly disturbing. We train control as a conditioned diffusion model where we adopt the normalized clip embeddings of the models as conditioning. So that's the text embedding model in clip, not the image embedding model in clip. Ablation study. So this is where they're going to remove different parts of their process and then see which part results in the best performance. So what is doing most of the heavy lifting? Demonstrated that the inclusion of conditioning and guidance leads to superior visual performance. So this classifier-free guidance concept is kind of where I guess they're getting most of their juice. However, if we only apply guidance on unconditional models, the generated outputs seem to have artifacts. On the other hand, when using the conditional model only, the model isn't able to recover all the details from the input image, especially the background. I think this is probably because the triplane latent does not include any details on the background, right? The triplane latent is coming out of... I already lost it, but the triplane latent is trained on only faces, so therefore it's going to basically learn to ignore the background. So it makes sense that it would suck at the background, or at least the diffusion would suck in the background. And then the related work section near the end, which I actually kind of like this. Sometimes this related work section gets put at the beginning, and I feel like it kind of slows down the paper reading, but you put it at the end because mostly what this is just a giant citation fest where you just kind of cite every single thing that you can. Key challenge here, obtain 3D ground truth. Most works tackle this by reconstructing 3D ground truths from dense multi-view data. Can be trained on only single view data by using a 3D GAN to synthesize. See, like, this is just straight up bullshit. It's like other people have to rely on 3D ground truth coming from dense multi-view data. We instead rely on a GAN which has been trained on 3D ground truth with dense multi-view data. So you can't say you're not using a thing if you're using a model that has been trained on that thing. So it's a little bit disingenuous here. Applies 2D diffusion priors from a sparse view reconstruction for text. Nerf diff applies test time optimization by distilling the 2D diffusion priors into nerf. Our focus is 3D aware image synthesis controlled by various control signals, and we apply denoising directly in 3D. I think that's really the key part of this paper is this weird triplane latent in which they denoise. Conventional GANs can generate photorealistic images from low-dimensionally randomly sampled latent vectors, that's the U vector, but have limited controllability. Follow-up works enable controllability by either adding conditioning input along with the sampled vectors as input, named conditional GANs, or manipulating the sampled vectors. Right. These works only focus on 2D image synthesis, but cannot explicitly control 3D properties. 3D GANs have been developing integrating 3D representations and rendering into GANs. While these models can control 3D properties by manipulating the latent vectors, the controllability is limited to global camera poses or geometry. And even that, like, global camera poses is a little bit generous, you know? Like, I wouldn't call these global camera poses. These camera poses, the distribution of these camera poses is so constrained. Right, pretty much every single one of these images is like a frontal shot from like half a meter away from the face. Other conditional 3D GANs for generated objects need additional constraints. However, their synthesis quality is still limited. Our method of prose allows a variety of control signals for fine-level 3D aware image synthesis on various kinds of objects. Conclusion. We propose Control 3 Diff, a versatile approach for 3D aware image synthesis that combines the strengths of 3D GANs and diffusion models. Our method enables precise control over image synthesis by explicitly modeling the underlying latent distribution. We validate our approach on standard benchmarks, demonstrating its effectiveness with various types of conditioning inputs. Control 3 Diff represents a significant advancement, I don't know about that, in generative modeling, opening up new research possibilities in this area. And that's it, guys. Do we got anything interesting in the appendices? Here's FFHQ, AFHQ, ShapeNet, CelebHQ, StyleGAN 3. Here's the actual model. The triplane dimension is this. 3 by 256 by 256 by 32. We constrain the values of the triplanes to -1 to 1 with tan H. So tan H, what that function looks like is like this, right? So if I put any number into tan H, if I put -infinity into tan H, I get -1. If I put infinity into tan H, I get 1. So tan H as a function will basically squash any -infinity to infinity number into -1 to 1. So they're using that constraint. So all of the values in this triplane are -1 to 1. And you notice how this triplane is 4-dimensional. And that's because the for each individual point in that triplane, you have 3 color channels, R, G, and B, which you can see right in all their examples here. The triplanes definitely have red, green, and blue on them. which one is the small dimension? It looks like the depth is the small dimension. So it's 256 by 256 and then 32. So maybe this one is the 32, the depth. What else we got here? Training. Gamma 1, gamma 0.3. What is this gamma? I think that's one of the hyperparameters that they had. We're going to have to scroll up. Here's what they're training it on. Batch size 32, 8 NVIDIA A100s, trains for 3 days on 25 million images. That 8 NVIDIA A100s is very popular. Trained EG3D models are used in both 3D diffusion, training, and inference. More precisely, we keep the neural renderer, so the actual nerf, which is, as they say, frozen. We adopt the center camera for GPC and input the EMA style vector W average as well as the constant noise to the upsamplers. Conditional model. Since the triplane size is fixed across various datasets, we apply exactly the same architecture for all experiments. I mean, this triplane, I wonder if it benefits or whether it's negatively impacted by the dataset distribution. I bet you the triplane only works because these datasets are so constrained. If you had a much more varied dataset, the triplane would probably be task specific. What else do we got here? Little Atom W optimizer, learning rate of 2e to the negative 5. Weight decay. Shifted cosine schedule. Little learning rate schedule there. Camera viewpoints from natural images are typically biased towards the center view. Kind of understatement of the century there. Found it crucial to have unbiased camera distribution when the 3D, like this, what do you mean? It's very biased. Augment the intrinsic matrix. Camera intrinsics are properties such as the fisheye look. Basically, it's like you have extrinsic camera matrix tells you where the camera is in the 3D world, and then intrinsic camera matrix tells you kind of the lens effects, the focus, the distortion, the fisheye, stuff like that. So they kind of do data augmentation in the camera by kind of messing with those intrinsic camera parameters. No classifier-free guidance is applied. What else we got? What else we got? Additional results, pix to pix, limitations. While learning from the latent space of GANs allows us to effectively learn controllable diffusion models, it also brings the drawbacks that GANs commonly have. For instance, a common artifact of the adversarial training is that the learned latent space typically has mode collapse, which in turn affects the 3D diffusion learning that it may not cover the full data space. You're limited to whatever that GAN learned. If that GAN is trash, this whole thing is going to be trash. Particularly notice this collapsing effect on synthetic datasets with complex geometries such as ShapeNet. Yeah, and I think that kind of goes to show what we were saying before, right? We were saying before where if you have a dataset that isn't extremely ordered like these face data sets. These face data sets are very, very consistent and similar, right? Like the camera pose distribution is almost identical. The position of the person and like everything is like super similar in these data sets. If you use a data set that's maybe a little bit more broad, a little bit more general, even something like this ShapeNet where you have chairs and laptops, it's going to make this kind of approach just way worse because this approach kind of relies on the fact that everything is kind of very similar. Look at these beautiful kitties here. And look, this cat looks a little grumpy. I like that. Pretty cool. A man. A man wearing glasses with a smile. Text prompts transform to normalized clipped embeddings with which the diffusion model directly conditions on. Cool, so that's it. Gotta head out soon, but that was, let's do a little paper summary here. Let me take a second. All right, so today we read Learning Controllable 3D Diffusion Models from Single View Images. This is a little bit older paper, but actually recommended from one of our Discord channel members. So if you have your own paper recommendations, feel free to go and drop them in there, and maybe we'll read them. So this is basically a diffusion model. So it's generating images, conditioned. It's a conditional diffusion model, so it's conditioned on a variety of different things. You can condition it on segmentation maps or edge maps or text. And really, the meat of this paper is this kind of 3D awareness that it has. And that 3D awareness comes through this triplane latent. So basically, they're using this GAN called EGAN. Where is it? EGAN, something like that. EG3D. So EG3D is a GAN, which is a generative adversarial network, which is basically a generator and a discriminator. It's two networks that basically learn to generate and then tell apart real and fake images. But here you're really just using the generator. And this GAN is special because it doesn't generate 2D images. What this GAN generates is it generates these triplanes, these three planes, which end up acting as the latent in which this diffusion model denoises. So you can see how basically the way that they came to this idea was that they were like, hey, latent diffusion models are popular. What if we picked a latent that had some kind of 3D prior built into it? And they were like, what kind of latent can we use that has a 3D prior built into it? And then boom, they came upon this GAN that creates these weird triplane latents. So these weird triplane latents can be turned into images using a nerf, and that's what this green R is. So that's basically what's going on. It's basically just a latent diffusion model that uses these weird triplanes that come from a pre-trained GAN. So all of that 3D knowledge is coming from this GAN that's been pre-trained itself on a bunch of other 3D data. So kind of a cool idea. I think that's interesting. But overall, I don't like this paper, you know. I'm gonna say overall kind of meh. And the reason is that, one, I think there's too many pieces here. I think you have this nerf, you have this generator, you have this discriminator, you have all the different parts of the diffusion model. There's like 10 different models in here. So loading all of this crap into like too many pieces. That's my first kind of critique. The second critique here is that you're limited by this pre-trained generator, or this pre-trained GAN here. Whatever biases have been fed into this GAN in order to create these triplanes, you're going to end up with the same biases affecting your model, right? And I think that the fact that they're limiting this to these like face data sets and basically the animal equivalent of these face data sets, these data sets, as soon as you see these, you should be suspicious, because the reason people use these data sets is that they're very narrow. They're basically almost identical in terms of camera poses, almost identical in terms of the appearance of them, the object-centricness of them, the consistency of, like, it's always a picture of a face, always has two eyes, always has the nose, always has the mouth, and mouth is almost at the same place, nose is almost at the same place, and so on. So anytime you're doing stuff on a very constrained data set like that, I worry about the ability of your technique of generalizing beyond that data set. And having this much complexity and this many pieces in a technique that is constrained to a specific tiny, narrow data distribution is kind of pointless, you know, because it's like, if you're going to have all this extra complexity, at least make it something that generalizes beyond what it's been trained on, but I don't think that's the case here. But yeah, that's all I got to say about that. Cool pictures. And I like that they use cats. I guess that's one thing I do like. I like it when they when you generate pictures of cats. So that's it. Thanks for the recommendation. You guys have a great Monday, and talk to you guys later.